Hello, Applied Physics. So today we're going to look at the concept of temperature. And so what we're going to answer the question now, what exactly is temperature? We use temperature every day, but what is it describing? So let's talk about that. So temperature, if something temperature indicates the presence of heat. So throughout this week, we'll look at the concept of heat a lot more closely than we'll look at temperature and talk about what heat means. What is heat? Internal energy. What is internal energy? Well, we kind of need a better definition because to describe internal energy, we need to learn about a whole bunch of other stuff, which we'll start tomorrow. So we kind of need a better different definition for what temperature is exactly. So let's break that word down. Okay, not like that. Let's try to help myself a little bit of corny humor. Okay, so temperature is the average kinetic energy of a material's molecules. So let's look at that definition word by word here. Average. So we know, so an average, a lot of you guys know what an average is. Let's say that we have a Sally, one person has $30, and then Joe has $20. Between the two of them, they have an average of $25, right? Nobody has $25. One person has 20, one person has 30, but the average amount of money that both people have is 25. It's in the middle. Of course, if you had added 10 more people and they all have different amounts of money, you could calculate an average amount of money for all of them. So that's what average is. That one's a little bit easy. Kinetic energy. You guys learned about this on last time on Thursday. If you're watching this lecture in term 4 of 2020, it was last Thursday, you guys learned about kinetic energy. Kinetic energy means something has motion, something is moving. So average, kinetic energy. Kinetic energy is the energy of something that's moving of a material's molecules. So hopefully at this point, you know that everything that you can see and touch and feel is made of molecules. So anything that has a temperature has some kinetic energy. That's what this definition is saying. So like even your body, even when you're sitting completely still, every single one of your molecules is moving. And you might not think that might not be too hard for you to believe because, well, you know that your body is made of cells and cells move all the time. Okay, well, think about even something ordinary. Think about like a glass of water. Or better yet, let me find something else. Highlighter. This highlighter has some temperature, right? This is at room temperature, which means that the molecules are moving. They're not, it's not like flying across the room moving, but they're vibrating at a very, very small scale that we can't see with our eyes. What this definition is saying is that these molecules are vibrating. So the temperature of this highlighter is the average kinetic energy of the molecules. What that's saying is that if I were going to take out the molecules of this highlighter one by one, some of the molecules would be moving faster, some of them would be moving slower. But on average, I can measure this temperature to about, I have my thermostat set to 65 degrees Fahrenheit. So hopefully this highlighter is about 65 degrees Fahrenheit as well. Okay. So if that didn't make sense, maybe rewind and watch that a couple times or look at the reading a few times too. That's what we mean by temperature. Temperature is the average kinetic energy of a material's molecules. Okay, so here's a question. Which has a higher temperature? Is it a boiling pot or a block of ice? Okay, it's not a trick question. A boiling pot has a higher temperature, right? Why? Because the average kinetic energy or the average motion of the pot's particles is higher. So what we're saying is that the block of ice and the boiling water both have molecules. But the boiling water, on average, those particles are moving a lot faster. Okay, good so far? So let's talk a little bit about temperature scales. So we kind of got a good definition of temperature. Let's look at different scales of temperature. So The scale that we're most familiar with here in the USA is Fahrenheit. I think we might be one of the fewest. There might be only three nations, or it might just be the United States. I don't know, that use Fahrenheit. It's actually not that common to use Fahrenheit elsewhere in the world. Um, so there's kind of four categories here. I'm going to come back to the last category of absolute zero, but we know that the freezing point of water is 32 degrees Fahrenheit. If you wake up one morning and it's 30 degrees Fahrenheit or lower than that, you know that there might be ice on your car. If it's above 32, there's probably not ice on your car. The average body temperature is 98 degrees Fahrenheit. If you're 100 or higher than that, that means you have a fever. Boiling point of water is 212 degrees Fahrenheit. So if you know we need to give your pot of water a lot of heat because it needs to get up to 212 degrees Fahrenheit before it'll start to boil, and you need to boil water for lots of different reasons. Um, and so that means that if you have a piece of metal and you know that piece of metal is 200 or 212 degrees Fahrenheit, you don't want to touch that because that's going to scald your hand, right? Okay, so that's Fahrenheit. We all know we've all worked with Fahrenheit. Let's compare that to a couple of other temperature scales. So I'm introducing these scales to you because you guys are going to look at these temperature scales this week. Celsius and Kelvin are really the scales that most scientists use. Again, that's because Fahrenheit is not a very common measurement of temperature. And scientists nowadays work with many different other, even if you're in the United States and you're a scientist or a physicist, you're working with other scientists around the world. Well, other scientists use Celsius or Kelvin. So in order to learn science, we need to learn about these other temperature scales. So just compare the freezing point of water, 32 degrees Fahrenheit, to Celsius, 0 degrees Celsius. Um, and actually, Celsius is based around water. Fahrenheit is kind of based around the freezing point and melting point of alcohol or something weird like that. Celsius is based entirely on water. For example, the freezing point of water is a nice round 0 degrees Celsius. That's how you define 0 degrees Celsius, is the freezing point of water at sea level. Same with, and 100 degrees Celsius is the boiling point of water at sea level. So whereas 100 degrees Fahrenheit for us might be like a nice hot day, 100 degrees Celsius, if it's that hot outside, we better not take a foot outside because that's hot enough to boil water. That's the equivalent of 200 degrees Fahrenheit. And so, and I forgot to put in my units there, average body temperature would be 37 degrees Celsius. So that's Fahrenheit, Celsius. Another one that you might not have heard of is Kelvin. So the reason Kelvin was invented was for this very first category, absolute zero. So absolute zero is the theoretical temperature at which molecules cease to vibrate. So you remember me telling you about how all molecules vibrate if they have a temperature? Well, we can have negative temperatures with Fahrenheit and negative temperatures with Celsius, but there is no such thing as a negative Kelvin temperature because 0 degrees Kelvin was set so that 0 Kelvin is the theoretical temperature at which it's so cold that no molecules can possibly vibrate anymore. That doesn't mean they can't have energy, but that just means they can't vibrate. And so if you look at the freezing point of water for Kelvin, it's 273 Kelvin. Average body temperature 310 Kelvin. Elva's boiling point of water is 373 Kelvin. So 310 anything sounds like a lot, but for Kelvin, since zero is set at the lowest temperature possible, 310 Kelvin, that's the average body temperature. That's just the way the scale works. So you can keep this table with you. You can write it down so you know for comparison. When somebody says 273 Kelvin, well, that sounds pretty hot, but actually that's pretty cold. That's the freezing point of water. Sorry, I'm watching one of my demonstrations crack over here. I'll show you what I mean in a second. So let's just have a little bit of fun here. Let's look at these temperature scales and let's ask, how would the average person do in these temperatures? So we have Fahrenheit, 0 degrees Fahrenheit versus 100 degrees Fahrenheit. Well, 0 degrees Fahrenheit, if you're watching this video and you're St. Louis, you know you've been out in temperatures at 0 degrees Fahrenheit, maybe colder. So that just means it's really cold outside. You can survive that. 100 degrees Fahrenheit, again, that's hot, but you can survive that. 0 degrees Celsius, well, if you remember from the table from the last the table that we had on the last page, 0 degrees Celsius, that's just freezing point of water. So that's the temperature at which water freezes at 30 degrees, 32 degrees Fahrenheit. So again, that's cold, but put a coat on, you're fine. 100 degrees Celsius, well, that's the temperature at which water boils. So you'd be dead. That's really hot. In fact, that's really hot. That's scalding hot. So yeah, you'd be dead. What about the average person at 0 Kelvin? Well, remember, that's the temperature at which nothing can move at all. So you would be frozen long before 0 Kelvin. So that's very, very cold. 100 Kelvin. Well, you'd say that, oh, 100, that sounds pretty hot. Well, remember, Kelvin is set, so 0 Kelvin is absolute zero. So it's not hot. It's still really cold. That's actually way colder than even the freezing point of water. So that's just kind of comparing Fahrenheit, Celsius, and Kelvin. Just a little bit of fun. If you think numbers are fun, a little bit of fun. Okay, last thing I'll say is on today's CK12 practice, I want you to let Google do the conversions for you. So there's going to be the CK12 is going to quiz you on a little bit of math today. I just want to let you know that you have my permission to use Google and not use the formulas for that math. So for example, if you get a question of, well, what is 37 degrees Celsius in Fahrenheit, or convert 37 degrees Celsius to Fahrenheit, all you need to do is go to Google and say 37C to F, and it will give you an answer. And let me see if I can show you that. So if I just type in, let me go to, oh, I already am on Google. So 37 Celsius to F, or Celsius to Fahrenheit, it gives you a little temperature converter. I want you to do those conversions, but I don't want you to have to use the formulas for those. We're going to do some math later this week, which is why I'm not having you do this math. This is really easy conversion math. I don't want you to take the time to go through the algebra and figure this out. Just use Google for those conversions. And that's all I have to say today, but I did skip one part. And so if you want to stick around for a little bit of bonus. So going back to this example, which was higher, which has a higher temperature, the boiling point of water, sorry, the boiling pot of water or the frozen block of ice? Well, it was the boiling pot of water, right? So I have here a frozen water bottle and just a regular glass of water. So I know that this is colder because, well, to me it feels colder, but that's not exactly why it's a colder temperature. So we're going to discuss later this week that what your skin is feeling is you're not feeling temperature. What your skin is feeling is heat. So this water bottle feels a lot colder, but it's not because I can feel temperature. It's because I can feel heat leaving from my hands. So when I say something is cold, that means the average kinetic energy of the molecules is low. So the molecules in this bottle of water are vibrating much more slowly than my fingers. That means that the heat from my hands wants to leave my hands and join the lack of heat in this frozen water bottle. And actually, this water in this glass is colder than my fingers too, but the average kinetic energy is much higher that I don't feel nearly as much heat leaving my fingertips and going into the glass of water. So a lot of that stuff we'll get into later this week, but I just kind of want to let you know what temperature is and what the feeling of heat is in your hands. Again, you cannot feel temperature. What you feel is heat. And I'll give you some more concrete examples later on this week, but that's what I want to share for you now. Again, don't forget, let CK12 do those conversions for you, and I'll try to leave a note. Hopefully the guys are watching these lectures. But that's all for now. Thank you for watching.